The Collatz conjecture is a deceptively simple mathematical trap. If a number is even, cut it in half. If it is odd, triple it and add 1. Routing any number through these simple rules seems to inevitably cascade it down to an endless looping basin of 4, 2, and 1. Mathematicians hypothesize that every starting number eventually falls here. We have verified this up to astronomical limits, but in the infinite world of mathematics, computation is not a proof. Even minor changes to this rule reveal why proving the conjecture is so incredibly difficult. Indeed, look at how fragile this system is. Under the standard 3n plus 1 rules, 27 takes a chaotic journey, but eventually falls to 1. But change the rule ever so slightly to 5n plus 1, and that very same starting point violently explodes toward infinity. This extreme sensitivity to tiny rules is the first clue that a global predictive theory of these sequences is extraordinarily elusive. To understand why, we can model this system as a mechanical feedback loop. The blue gear halves even numbers, while the red gear scales odd numbers up. This sets up a dynamic mathematical tug-of-war. A starting number like 6 is pulled back and forth between these gears, transforming into 3, then 10, and 5, until it finally hits 16, a perfect power of 2. From there, it is caught in a frictionless descent straight to 1. But does this invisible gravity catch every integer in the universe? The truth is, the machine's behavior changes completely based on where you start. Clean powers of 2 collapse immediately, whereas a prime like 7 zigzags stubbornly through the gears. Just next door, 27 explodes into an incredibly complex 111-step flight before landing. This wild, chaotic variety means we cannot easily group numbers together by how they behave, making a universal proof exceptionally difficult. Intuitively, you might think larger starting numbers always take longer to collapse, but physical magnitude is a terrible guide here. While the massive 32 falls to 1 in a few instant steps, the much smaller 7 undergoes a chaotic, prolonged cascade. This disconnect between a number's size and its historical trajectory shows that local properties tell us almost nothing about global behavior. What if we tried to work backward, reverse the Collatz rules, and we can build a tree of numbers growing outward from 1? Every branch we sprout is a guaranteed, proven pathway back down to our target basin. Each node represents a concrete number settled, and as the tree grows to capture wild nodes like 27, it seems it should span the whole number line. Yet the central mystery persists. Does this infinite tree eventually capture every single integer, or are some numbers completely isolated, left out in the cold? The global stability we observe in the original rule may just be a statistical miracle. If we slightly adjust our odd gear to 3n minus 1, the structure of the mathematical space instantly fractures. Starting with 7 no longer leads to 1. Instead, it is captured by a completely independent 5-number looping basin. This reveals that the solitary cycle of our original system might be a rare, delicate exception. On the surface, these two rules are virtually identical, differing by a single, tiny sign. Yet, in mathematics, proximity in form does not mean similarity in outcome. For 13, the +1 rule cascades seamlessly to 1, but the -1 rule traps it in a loop forever. This is the heart of the Collatz problem. Lacking a global proof, we cannot guarantee that even a tiny change hasn't entirely rewritten a number's fate. To find a deeper pattern, we can look at the average trend. On average, any odd number in the system is immediately followed by an even division. This means odd steps don't just triple numbers. They effectively scale them by 1.5 over 2 steps. This is balanced against the straight halving of even steps, setting up a quantifiable tug-of-war on our growth gauge. To see which side wins, we have to calculate the overall rate of decay. We can measure the long-term trend of these random-looking steps by taking their geometric average. If even and odd steps are equally likely, then half the time the system multiplies by 1.5, and the other half it multiplies by 0.5. Their average rate of change per step is the square root of their product, roughly 0.87. Because this is less than 1, the mathematical landscape contracts, suggesting everything should eventually shrink downward. But is a statistical average enough to prove that no number escapes? To test this, let's intentionally tip the scales. By shifting to a 5n plus 1 rule, odd steps now multiply by 2.5. Combined with halving, the geometric average rises to the square root of 1.25, about 1.12. Because this average is greater than 1, the system expands, and numbers generally explode toward infinity. In this regime, growing averages suggest most paths escape. But here is the critical warning. When we return to our 3n-1 system, it inherits the exact same decaying average of 0.87 as our original rule. Most numbers do indeed collapse, yet we know that a subset gets permanently trapped in alternative loops. A statistical average can state the general drift of a population, but in discrete math, an average trend is powerless to rule out these local structural exceptions. This reveals the profound gap between heuristics and absolute mathematical proof. Continuous math formulas show an average decay of 0.87, expecting every path to erode to nothing over time. But of course, numbers are discrete entities. A single local loop can act as a permanent, logical trap, snaring individual paths forever. Statistical likelihood is simply not the same as logical certainty. What if we tried to bypass these linear traps by changing the operations entirely? Nonlinear systems, like the juggler sequence, use fractional exponents to dramatically compress growth. By swinging a number between square root and cubic power rules, the dampening effect is so severe that a number like 15 collapses to 1 in just 4 steps. Compare that to the marathon 111 steps needed under Collatz, showing how structural math changes reshape everything. The original Collatz system is partitioned simply by even and odd, modulo 2. But we can generalize this concept by partitioning numbers modulo 3, routing them through 3 distinct gears with 3 customized rules. A simple input like 7 now bounces between these remainder classes, climbing rapidly into the thousands. By adding more gears, we construct what is known as a generalized Collatz map, unlocking a playground of extremely chaotic and unpredictable behavior. By scaling this up to many gears, we can program these generalized Collatz machines to simulate any computer program. But this computational power comes at an ultimate price. In 1972, John Conway proved that generalized Collatz systems are undecidable. There is no master algorithm that can ever predict whether a given starting number will eventually collapse or escape. If the general problem is mathematically unprovable, could our simple original rule also lie beyond the reach of human logic? Conway's proof revealed that basic arithmetic is actually a universal programming language. We can construct a system called FRACTRAN, where multiplying an integer token by a list of simple fractions runs a program that outputs the prime numbers as exponents. If simple multiplication can generate the complex, erratic sequence of primes, then predicting the fate of these arithmetic trajectories is equivalent to solving the deepest mysteries of number theory. This is why empirical testing has hit a wall. Even if computers verify the Collatz conjecture up to 2 to the 68th power, we are searching a microscopic drop in an infinite ocean. Each confirmed number settles safely at 1, but an infinite landscape of unchecked numbers lies just beyond, completely immune to our computational search. The Collatz conjecture is likely just a single visible pixel in a vast, infinite landscape of similar mathematical systems, most of which we now know are fundamentally undecidable. Perhaps we cannot prove it not because we haven't tried hard enough, but because this deceptively simple arithmetic loop is our first glimpse of the unknowable.